A very good morning, students. In today's class, I will be talking about group 2 elements, that is the S block of elements, and they are also known as the alkaline earth metals because they are basic in nature and they are found in the earth crust. Now, the group 2 elements that we are known are they begins with beryllium, magnesium, calcium, strontium, and barium are the elements. And what's so specific about these elements? The specificity of these elements is that their outermost shell has got only 2 electrons. That is, the configuration is LS2. That is, you would have a maximum of 2 electrons in the outermost shell, and the outermost subshell would be the S subshell. So there are 2 electrons. Moving ahead, let's talk about a few physical properties which are of importance in the group 2. The first property is flame coloration. As the word says, they impart peculiar colors to the flame when they are introduced into the flame. Now, the reason is, out of the flame coloration, your beryllium and magnesium do not show any flame coloration, while the rest, that is calcium, strontium and barium, their salts, they show flame coloration. This shows a brick red coloration, while strontium shows crimson red and barium shows an apple green color of flame. Which means, when you introduce these salts into the flame, these elements have a low ionization energy. It is this low ionization energy which causes their outermost electron to be excited due to the flame. So, when you introduce your salt in the form of a chloride, because they are more volatile, into the flame starts showing you the colors. So, if you have a barium salt, you would find the flame turning green in color. And the reason for this green color is that the outermost electron of the barium, which is loosely held by the energy of the flame, gets excited to a higher orbital, and when this falls back, this gives the energy in the visible region. And when it gives the energy in the visible region, you observe the colors. Now, this excitation of the electron is only possible for larger metal ions, that is for calcium, strontium and barium. While beryllium and magnesium do belong to the same group, but they do not show any flame coloration owing to their small size, a very high ionization energy, and this ionization energy, for one, the flame is unable to excite the electron, and for second, if the electron does fall back, the light that it emits is not in the visible region. Moving to the second important property, which is the hydration energy. In case of the hydration energy refers to your metal ion, and taking it as 2 positive, is attracted by water. This is the water molecule. Oxygen having a delta minus and this having a delta positive due to the difference in their electronegativities. This I would represent it like this. This is the minus part, these two are the positive terminals. So your metal ion is attracted by water molecules like this, where the negative part of the water is attracted towards the metal ion. And this hydration is directly proportional to the charge of the ion upon the radius of the ion. So it is proportional to the charge upon the radius ratio. As you very well know, group 2 elements are smaller as compared to group 1. Number 1. So the radius becomes less, so the hydration should be higher. Also, the charge of group 2 members is 2 positive and that of group 1 members is 1 positive. So the charge is higher, radius is smaller, hence the hydration energy in case of group 2 is higher than group 1. So your group 1 member have a lower hydration than group 2 member. This result would be of help to us in the other properties also. Moving to the chemical reactivity. Let's compare again the group 1 and the group 2. Now both group 1 and 2 are metals. If they are metals, they have a tendency to lose electrons. How many? This would lose only 1 electron, while this would prefer to lose 2 electrons. This would require ionization energy 1. Only 1 electron is to be lost. Whereas this would require ionization 1 plus ionization 2, because you have to lose 2 electrons out of this metal. You have to pull out 2 electrons, and always, as you very well know, second ionization energy is always higher. So the net value of ionization energy is going to be very high. Since the electron removal from group 2 members is difficult, their compound formation becomes difficult, so their reactivity becomes less. Hence, if you compare the reactivity, group 1 members are more reactive than group 2 members. Moving ahead. Let's talk about the reaction with air. Coming to the chemical properties, let's talk about the reaction with air. When we talk about air, we are talking about oxygen and nitrogen gas, which is the major component in the air. Beryllium reacts with oxygen to form beryllium oxide. Magnesium reacts to form magnesium oxide. Beryllium also can form a beryllium nitride. Magnesium also can form a magnesium nitride. But it is this oxide film which is coated over these two metals that makes it unreactive. So your beryllium has an oxide layer. Your magnesium metal also has an oxide layer, which does not allow it to be reactive. The rest of the members, if we talk, they have a higher reactivity. The reason is their ionization energy is low. They can easily lose their electron and combine with the oxygen. Let's talk about reaction with halogens. What are halogens? Your fluorine, chlorine, bromine, iodine are the halogens, members belonging to group number 17, which are represented as X2 as Jan. The metal this time is of group 2, so it is going to lose 2 electrons. Hence, it has valency of 2. So your compound form would be MX2. Now this MX2 is normally ionic. Now why did I use the word normally ionic? The reason is the first member, if this was beryllium, then this compound will not be ionic. Beryllium compounds are covalent in nature. Why so? Because of its small size, very high ionization energy, it does not easily lose the electron, it prefers to share the electrons. And if it is sharing the electrons, the compound formed has to be covalent. If I talk about the halides of magnesium, this is my magnesium fluoride, magnesium chloride, magnesium bromide and magnesium iodide. All of them would have an ionic character, and if we talk about the ionic character, our aim is to check which is most ionic. To check which is most ionic, what is an ionic bond? An ionic bond is when an electron is transferred from the metal to the non-metal. Now in these cases the metal remains the same. If the metal is same, it can easily lose the electron, and that is the common factor in all the 4 compounds. Now talking about the non-metal, which non-metal do you think will easily accept the electron? Has to be the smaller non-metal. Which is the smaller non-metal? Fluorine. Fluorine is also the most electronegative element. Hence, the transfer of electron would be easiest in this case. So the ionic character would be maximum in this case. So that's the order for ionic character of the halides of magnesium. Coming to the chlorides of group 2, and they are hydrated. As we did, hydration energy is the cause for group 2 members to be hydrated, and hydration is directly proportional to the charge upon radius. Now looking at these, what do they have as a charge? They are all belonging to group number 2. So their charge will be +2. What about the radius? As I move down, what is happening to the radius? The radius is increasing. If the radius is increasing, the denominator is increasing. If the denominator is increasing, the hydration is going to be less, and that is evident. This exists with 8 water molecules. This exists with 6 water molecules. This also exists with 6 water molecules, perhaps owing to the presence of the 3D. And this exists with only 2 water molecules. So it is evident as we move down, the hydration is less because the radius is increasing. If the radius is increasing, then the charge density goes on decreasing. The charge as it is same, but the radius is increasing, so the hydration will go on decreasing as proved by the hydrated salts. The solubility of the fluorides of group 2. Now talking about the solubility of the fluorides, whenever we use the word solubility, we need two things. One is lattice energy, the second is hydration energy. Lattice is the energy required to break the inter-ionic forces in the crystalline solid, whereas hydration energy is the energy which is released when water molecules interact with the ions. So this is normally the energy required, while this is the energy released. So if your energy required is more, then the process is not going to be spontaneous, so it will not be soluble. So the requirement for solubility is that hydration energy should be greater than lattice energy. Only then do we have the salts to be soluble. Talking about fluorides, the solubility of fluorides is low. If I say the solubility is low, then the quick answer would be that either the hydration is less or the lattice is more. Now in this case, we very well know, in case of fluorides, the lattice is very high because of the small size of the anion. Smaller sized anions and cations, they tend to form a stronger interaction. So the lattice enthalpy is going to be very high because the lattice is because of the ionic bond. And ionic bonds are stronger with more non-metallic elements. So fluorides form strongly ionic compounds, hence their lattice energy is very high. That's the reason that the solubility is low, because fluorides have an extremely high lattice energy. Now talking about beryllium. Now beryllium is an element with 2 electrons in the outermost shell. Now what kind of a compound will it form with fluorine? The expected compound formed with fluorine with 7 electrons in the outermost shell would be something like this. 1 electron transferred here, the other electron transferred here, leading beryllium to become 2 positive and your chlorides become negative. Now what I have drawn is not the case. Why so? Because removing these 2 electrons is very tough. Why is it tough? Because the size of beryllium is very small. Since the size is very small, the removal of electron is going to be very difficult. And if the removal of electron is very difficult, the amount of energy required to remove is going to be very high. So it would not easily lose the electron. So this is never formed. It is not an ionic compound. In fact, beryllium compounds are covalent in nature. And what exactly happens in case of beryllium chloride? Now when we talk about beryllium chloride, the formula is BeCl2. But the structure is beryllium forming 1 covalent bond with Cl this side, the other covalent bond with Cl this side. And this is a covalent compound where beryllium has 2 electrons of its own, one from this chlorine, one from this chlorine, so it has got only 4 electrons. Hence it is electron deficient. Hence it is electron acceptor. If it is an electron acceptor, therefore it would be a Lewis acid. So your beryllium compounds are normally Lewis acid in nature. Now beryllium exists as this monomeric. Monomeric means single unit, only if it is in the gaseous state. What happens if I talk about beryllium chloride in solid state? In solid state, the beryllium chloride molecules will move closer, and if they do so, this is exactly what happens. Each beryllium has 2 chlorides around it. I am not drawing it linear because of a reason. Each beryllium has something like this. Now, to satisfy its octet, this beryllium pulls this beryllium chloride towards itself, and the lone pair of this chlorine are given towards the beryllium. Now, this beryllium has 2 plus 2, 4 plus 2, 6 plus 2, 8 electrons around it, 2 via covalent bonds and 2 via coordinate bond. And this continues. From here also, from the other 2 Cl atoms of the other molecule, you would have a polymeric chain formed. chain which has bridged Cl atoms. Fine. Moving ahead. Reaction with acids. What are acids? Acids, according to anomalies, are proton donors. So, when the proton is donated, this leads to a Cl minus and an H plus. Your magnesium, let the element be magnesium, and the metal magnesium, if it is magnesium, then in that case the compound form would be MgCl2 and the byproduct would be hydrogen gas. And of course there is some amount of heat released in the process because it is exothermic. Now in case the heat is large, there might be an explosion. When would the heat be large? When the element easily loses electrons. That means I am talking about the last member barium. But if the element is higher up in the group, then in that case hydrogen is still released, but the heat is not that much. So if you have water with you, if you have HCl with you and you add a piece of calcium or magnesium, adding a piece of calcium or magnesium, it is found that these hydrogen gas bubbles stick to it and it then starts to float on the surface. This we've done in class 10. Some metals do float on the surface of water owing to these hydrogen gas evolution, and the heat is not that much that it will lead to an explosion. Coming to the next property, which is reducing nature. This would be my last property in this class. I will be continuing in the part 2 of the lecture. Reducing nature. Now what is reducing nature? To reduce others. What is reduction? Gain of electron. So reducing agent is directly proportional to loss of electrons. As you can sense, out of group 1 and group 2, which will easily lose electron? The common answer is group 1. And what's the reason? Only 1 electron is to be lost. But that is not the reason. The reason why group 1 members are better reducing agents is because their sizes are large as compared to group 2. Also, their ionization energy is low. So they can easily lose electron as compared to group 2. Therefore, when you talk about reducing character, group 1 is a better reducing agent. Now presently, since we are focusing on group 2, let's talk about the standard reduction potential values. What do I mean by standard reduction potential? E0 value, as we did in redox reactions. Reduction means your metal N2 positive has to go to N. This process of gain of 2 electrons has a negative value. Whenever standard reduction potential is a negative value, means the process is not happening. The direction of the process has to be reversed. This negative value indicates that metal will prefer to go to metal 2 positive. Hence, it would lose electrons. More the negative, easier the loss of electron. If this happens, so if it is more negative in value, it is a better reducing agent. Done? So since the group 2 members have a negative value of standard reduction potential, they are good reducing agents as can be observed by these values. Talking about the standard reduction potential for beryllium ion, magnesium ion, calcium ion, strontium ion and barium ion. As I move down the group, we find that the elements are getting, values are getting more negative. So down the group, the value is more negative, therefore they are acting as better reducing agents. That was my last property for the alkaline earth metals in group number 2. We'll move with the next properties in our next class. Thank you. Bless you all.